Look up at the night sky, and you'll see countless stars shining like tiny pinpricks of light. But hidden among them are some of the most stunning and mysterious objects in the universe: planetary nebulas. These cosmic masterpieces aren't planets at all, despite their name. Instead, they're the glowing, often ghostly remnants of dying stars, painting the darkness with swirls of color and shapes so intricate they seem almost impossible. Imagine a star after billions of years of burning bright, finally exhaling its last breaths into space, leaving behind a dazzling shroud of gas and dust that glows with otherworldly beauty. That's the magic of a planetary nebula, a fleeting, radiant farewell etched across the cosmos. What makes these celestial wonders even more fascinating are the secrets they hold. Astronomers have spent decades unraveling their mysteries, only to stumble upon discoveries that defy expectations. Some nebulas twist into bizarre, unexplained shapes like cosmic jellyfish or hourglasses spinning in the void. Others hide rogue planets or strange chemical signatures that shouldn't exist. And then there are the ones that seem to pulse with energy, as if the star at their heart isn't quite done yet. Every new observation peels back another layer, revealing just how much we still don't understand about these stunning structures. So why do planetary nebulas captivate us so deeply? Maybe it's because they're cosmic storytellers, offering glimpses into the fate of our own sun billions of years from now. Or perhaps it's the sheer artistry of their forms, each one unique, sculpted by forces we're only beginning to comprehend. Today, we're diving into 30 of the strangest, most awe-inspiring discoveries about these celestial phenomena, from their mind-bending structures to the secrets buried in their glowing cores. By the end, you'll see the night sky in a whole new light, because once you know what's lurking out there, the universe becomes a far more mysterious and wondrous place. Ready to explore? Let's begin. The Butterfly Nebula isn't just a cosmic spectacle, it's a full-blown enigma. Stretching its glowing wings across the void, this celestial butterfly, also known as NGC 6302, defies everything we know about how planetary nebulas should look. Most of these stellar remnants form elegant spheres or gentle spirals, but the butterfly, it's a frenzy of twin lobes, jets of gas screaming outward at speeds over 600,000 miles per hour, creating a silhouette so distinct it could only be described as nature's grandest Rorschach test. So what sculpted this otherworldly shape? The leading theory points to a dramatic dance of binary stars. Imagine a dying star locked in orbit with a companion, its final gasps distorted by gravitational tugs and swirling magnetic fields. As the star shed its outer layers, the companion star may have funneled the ejections into those iconic wings, like a cosmic potter shaping clay. But here's where it gets stranger. Some observations suggest the central star might have been one of the hottest ever recorded, with surface temperatures soaring above 400,000 degrees Fahrenheit. That kind of heat doesn't just bend the rules, it shreds them, leaving astronomers questioning how such extreme conditions could even arise. Then there's the mystery of the nebula's spine, a dense, dusty waistline pinching the center like an hourglass. Infrared images reveal complex organic molecules embedded there, substances we'd normally associate with the birth of life, not the death of a star. It's as if the Butterfly Nebula is teasing us, blending destruction and creation into a single, bewildering masterpiece. Every time we think we've unraveled its secrets, it flutters just out of reach, reminding us that the universe has a flair for the dramatic. If the Butterfly Nebula left you breathless, wait until you meet its fiery cousin, the Red Spider Nebula. This cosmic arachnid, officially known as NGC 6537, isn't just a visual marvel, it's a battlefield of extreme forces. Picture a star's dying fury channeled into supersonic winds, racing through space at over 300 kilometers per second, fast enough to streak from Earth to the Moon in under 20 minutes. These aren't gentle breezes, they're tsunamis of ionized gas, carving the nebula's delicate filaments into a sprawling web that glows with eerie crimson light. At the heart of this chaos sits one of the universe's most relentless engines, a white dwarf star seething with radiation. While most dying stars fade quietly, this one's death throes are anything but peaceful. Its ultraviolet fury shreds the surrounding gas, heating it to millions of degrees and accelerating it outward in chaotic jets. The result, a labyrinth of filamentary tendrils, each one a roadmap of the star's explosive tantrums. But here's the twist, those filaments aren't just random squiggles. Hubble's razor-sharp images reveal symmetrical patterns, as if the winds are dancing to some unseen cosmic choreography. Astronomers suspect the white dwarf's magnetic field acts like an invisible sculptor, twisting the ejections into those intricate designs. Yet the real shocker lies in the chemistry. Spectrographs have detected bizarre molecules like hydrogen fluoride, a compound so reactive it's practically unheard of in space floating within the nebula's strands. It's as if the Red Spider is brewing cosmic poison in its web, challenging our understanding of how elements behave under such extreme conditions. And with temperatures at its core hotter than most supernova remnants, this nebula isn't just defying expectations, it's rewriting the rules of stellar death. Every strand of its glowing web whispers a question: how can something so beautiful be born from such violence? The Ring Nebula might be one of the most recognizable cosmic icons, but its familiar shape is a cosmic illusion. What appears as a perfect celestial smoke ring through amateur telescopes transforms into something far more intricate under Hubble's gaze. This isn't just a ring, it's a barrel-shaped labyrinth of glowing gas, with delicate loops and clumps swirling in 3 dimensions like a stellar lava lamp frozen mid-motion. At first glance, M57 seems deceptively simple, a glowing donut suspended in the void, but peel back the layers and you'll find chaos masquerading as order. Hubble's ultraviolet eye revealed fluorescent tendrils stretching far beyond the main ring, ghostly filaments that trace the nebula's violent birth. These aren't random wisps, they're shockwaves from the dying star's final eruptions, preserved in gaseous form like fossilized stellar screams. The real magic lies in the knots, scattered throughout the nebula like cosmic confetti. These dense clumps of gas defy expectations. Some stretch light years long, twisted into braids by magnetic fields stronger than anything near our sun. Others glow with unexpected elements like helium and nitrogen, hinting at chemical reactions we've never witnessed in labs. The most surprising, their symmetry. Despite the nebula's turbulent origins, these knots arrange themselves with eerie precision, lining up along the barrel's interior like pearls on a necklace. What created this impossible architecture? The leading theory involves a stellar death unlike any textbook model. Instead of shedding its skin in steady pulses, the central star may have ejected material in frantic bursts, each eruption colliding with previous ones at different angles. Imagine a firework exploding inside a hall of mirrors. Now replace the mirrors with shockwaves and the sparks with superheated plasma. That's the Ring Nebula, not a peaceful farewell, but a star's final fireworks display written across light years of space. Yet the biggest revelation might be what this means for our own solar system. The Ring Nebula's complex structure suggests dying stars don't follow predictable scripts. When our sun reaches its final act billions of years from now, its swan song could be just as unpredictable, a reminder that even in death, stars refuse to play by simple rules. The Helix Nebula doesn't just drift through space, it watches. Known as NGC 7293, this celestial structure stares back at us with an uncanny resemblance to a giant cosmic eye, its vibrant rings and ghostly glow earning it the unsettling nickname, the Eye of God. But its eerie appearance is just the beginning of the mystery. This nebula, one of the closest to Earth at just 700 light-years away, holds secrets that challenge our understanding of stellar evolution. At its core lies a white dwarf, the smoldering remnant of a sun-like star. What makes the Helix so mesmerizing isn't just its haunting gaze, but the hundreds of strange, comet-like knots dotted throughout its expanse. These aren't your average cosmic debris. Each one is a colossal clump of gas and dust, some stretching twice the diameter of our solar system. Picture massive, glowing teardrops, their tails streaming away from the central star as if caught in a stellar wind. But here's the puzzle: these knots shouldn't exist. According to conventional models, the intense radiation from the white dwarf should have vaporized them long ago. Yet there they are, defiantly intact, like cosmic survivors refusing to fade. The symmetry of the Helix adds another layer of intrigue. Unlike the chaotic swirls of other nebulas, this one boasts near-perfect concentric rings, as though sculpted by an invisible hand. Some astronomers speculate that an unseen companion star, a hidden dance partner, could be shaping the nebula's structure with its gravitational pull. Others suggest magnetic fields or even shock waves from the dying star's final outbursts might be responsible. But the truth, we still don't know. Perhaps the most haunting detail is what the Helix reveals about our own future. In a few billion years, our sun will meet a similar fate, shedding its outer layers in a final, radiant display. Will Earth one day find itself orbiting inside a nebula like this, bathed in the glow of its own dying star? The Helix doesn't answer. It just stares, silent and knowing, a reminder that even in death, the cosmos keeps its most profound secrets close. The Cat's Eye Nebula doesn't just stare back at us, it whispers secrets in concentric echoes. NGC 6543, as it's formally known, is one of the most complex planetary nebulas ever observed, and its hypnotic layers of gas tell a story of celestial violence written in perfect intervals. 11 distinct shells ripple outward from its core like tree rings carved by cosmic fire, each one a fossilized record of the dying star's final tantrums. These aren't random outbursts. Every 1,500 years, like clockwork, the star at the heart of the Cat's Eye expelled another shell of superheated material, a pulse so regular it challenges everything we know about stellar death. Picture a giant blowing smoke rings into space, each eruption sculpted into near-perfect spheres by forces we're still unraveling. What could trigger such precise cosmic hiccups? Some theorists point to a binary companion, its gravitational tugs yanking material from the dying star in rhythmic bursts. Others suggest the star's own magnetic fields, twisting and snapping like overstretched rubber bands, could fling material outward in these eerie cycles. But the real shock lies in the chemistry. These shells aren't just hollow bubbles, they're layered with elements like oxygen, nitrogen, and hydrogen, each ring a time capsule of the star's changing composition as it died. The outermost shells, older and cooler, glow faintly with the star's early ejections, while the inner ones, searing with trapped radiation, pulse with heavy metals forged in the star's final convulsions. It's as if the Cat's Eye preserved its own autopsy report, written in light and gas. Then there's the nebula's infamous central eye, a tangled knot of shockwaves and magnetic chaos where these orderly shells collapse into turbulence. Here, the star's most recent eruption plowed into previous ejections at hypersonic speeds, crumpling the once-perfect rings into jagged filaments. This violent core defies the nebula's serene outer beauty, proving even the most precise cosmic clocks eventually shatter. What does this mean for other dying stars? The Cat's Eye suggests stellar death might follow hidden rhythms, with pulses locked in celestial timekeepers we've only begun to notice. And if that's true, the universe's grand finale might be far more orchestrated and far stranger than we ever imagined. Deep in the constellation Centaurus lies a cosmic anomaly so cold it defies the very fabric of space, the Boomerang Nebula. Clocking in at a bone-chilling negative 272 degrees Celsius, this expanding cloud of gas holds the record for the coldest natural place in the known universe. That's just 1 degree above absolute zero, colder than the background temperature of space itself, and colder than any lab experiment on Earth has ever achieved. What creates this extreme deep freeze? The answer lies in the nebula's breakneck expansion. Imagine a dying star ejecting its outer layers at speeds over 165,000 kilometers per hour, so fast that the gas doesn't just drift away, it practically explodes outward. This violent stretch cools the nebula's molecules like a cosmic refrigerator, sapping their energy until they're barely moving at all. The effect is so dramatic that even the faint afterglow of the Big Bang, which permeates all of space, can't warm it up. But here's where it gets stranger. The boomerang isn't just cold, it's asymmetrical. Unlike the neat rings or spirals of other planetary nebulas, this one forms a lopsided bow-tie shape with two uneven lobes stretching into the void. Hubble's images reveal intricate patterns within those lobes, like frozen ripples in a pond, each one a snapshot of the star's death throes. Some astronomers think a hidden companion star might be warping the outflow, while others point to magnetic fields twisting the ejections into this bizarre form. The real shock came when telescopes detected carbon monoxide molecules within the nebula, molecules that should have been destroyed by the central star's radiation. Instead, they're preserved in this cosmic icebox, their light stretched and dimmed by the extreme cold. It's as if the Boomerang Nebula pressed pause on the laws of physics, creating a pocket of the universe where time itself seems to slow down. What does this mean for our understanding of stellar death? The Boomerang challenges the idea that all planetary nebulas are hot, glowing remnants. Instead, it reveals a universe where stars can leave behind not just fire, but ice, a ghostly, frozen whisper of what once burned bright. The Southern Crab Nebula doesn't just sit quietly in the cosmos, it erupts with symmetrical fury. Officially catalogued as He2104, this celestial spectacle looks like something straight out of a sci-fi fantasy. Twin jets of gas, perfectly mirrored, blasting outward to form an hourglass so precise it seems artificially crafted. But the real magic isn't just in its shape, it's in the hidden dance of stars that created it. At the heart of this nebula lies one of the universe's most volatile relationships, a symbiotic star system. Picture a fiery tango between a red giant and a white dwarf, locked in a gravitational embrace so intimate it borders on destructive. As the red giant sheds its outer layers, the white dwarf greedily steals material, funneling it into an accretion disk. But this cosmic theft isn't tidy. When too much gas piles up, the system erupts in a thermonuclear tantrum, launching jets of material at speeds that defy logic. These aren't gentle streams, they're supersonic scythes, carving the nebula's iconic claws with laser-like precision. What's truly baffling is how these jets maintain their symmetry across light years. Most stellar outbursts are chaotic, yet the Southern Crab's ejections curve in flawless arcs, like twin serpents rising from a cosmic chalice. Astronomers suspect magnetic fields act as invisible guides, shaping the flows with forces we can't yet measure. But even that theory stumbles when confronted with the nebula's intricate knots, dense clumps of gas strung along the jets like pearls on a necklace, each one a puzzle of stability in a maelstrom of energy. Then there's the timing. Unlike the cat's eye's rhythmic pulses, the Southern Crab's eruptions seem sporadic, with evidence of multiple outbursts layered like chapters in a violent history. Hubble's snapshots reveal ghostly echoes of past explosions, their remnants glowing faintly around the newer, brighter structures. It's as if the nebula refuses to let its past fade, preserving every eruption in luminous detail. But the most haunting question remains: are we witnessing a prelude to catastrophe? With the white dwarf continually feeding, some calculations suggest it could eventually reach critical mass, triggering a supernova that would rewrite the nebula's story in a single, blinding flash. For now, though, the Southern Crab keeps its secrets, its hourglass ticking silently in the void, a reminder that even the universe's most beautiful structures are born from chaos. Meet the Eskimo Nebula, a cosmic enigma wrapped in what looks like a celestial parka. officially catalogued as NGC 2392. This stunning structure earned its nickname from the thick, fur-like filaments swirling around its central star, resembling the ruff of a winter hood. But this isn't just a pretty cosmic coat. Those filaments are clues to one of the most violent stellar breakups in the galaxy. What creates this intricate, tangled web? The leading suspect is gravitational sabotage. Imagine a dying star not alone but locked in a turbulent dance with a hidden companion. As the primary star swelled into a red giant, its outer layers became vulnerable, stretched and torn by the smaller star's relentless tug of war. The result, a chaotic ejection of gas, whipped into those iconic filaments by competing forces like a cosmic blender churning stardust into delicate strands. Hubble's razor-sharp vision reveals these filaments aren't random. They spiral outward in precise, almost artistic patterns, some stretching light years long while others curl into tight knots. Infrared observations add another twist. Embedded within them are complex hydrocarbons, molecules more commonly found in the birthplaces of planets than in the graves of stars. It's as if the Eskimo Nebula is mocking the line between creation and destruction, weaving the building blocks of new worlds from the ashes of an old one. But the real mystery lies at the core. The central star, now a searing white dwarf, blasts its surroundings with radiation so intense it should have vaporized those filaments eons ago. Yet there they stand, defiantly intact. Some astronomers theorize magnetic fields act as invisible shields, cocooning the filaments from the star's fury. Others suggest the companion star might still be stirring the pot, its gravity shepherding the gas into stable formations. Then there's the nebula's eerie symmetry. Unlike the butterfly or red spider's chaotic beauty, the Eskimo's filaments radiate evenly like spokes on a wheel, a level of order that seems impossible amid such stellar turbulence. This isn't just a dying star's farewell, it's a carefully staged exit orchestrated by forces we've only begun to decipher. So what does it all mean? The Eskimo Nebula challenges our assumptions about how stars die, proving even in their final moments they can craft structures of breathtaking precision. And if a single star with a pesky companion can create something this complex, imagine what other cosmic collaborations might be hiding in the dark. The Ant Nebula doesn't just crawl across the cosmos, it defies it with surgical precision. Catalogued as MZ3, this celestial insect earned its name from two impossibly symmetrical lobes that stretch outward like an ant's segmented body, each one a flawless mirror of the other. But this isn't just another pretty cosmic shape. It's a riddle wrapped in ionized gas, challenging astronomers to decipher how nature crafted something so meticulously balanced. What carved these perfect lobes? The debate splits scientists into two camps. On one side, there's the binary star theory. Imagine a dying star locked in orbit with a companion, its final gasps funneled into twin jets by the companion's gravitational pull like a cosmic faucet twisting water into two spiraling streams. Supporting this idea are the nebula's high-speed outflows, clocking in at over 3.5 million kilometers per hour. Speeds so extreme they'd almost certainly require a second star's gravitational slingshot. But then there's the magnetic camp. Picture the dying star's own magnetic field, wound up like a spring during its death throes, suddenly snapping taut and ejecting material along two rigid polar paths. Observations reveal faint, thread-like structures within the lobes, aligning like iron filings around a magnet, hinting at invisible forces sculpting the chaos. The real twist, the Ant Nebula's core is a masterclass in cosmic contradiction. At its heart lies one of the hottest white dwarfs ever recorded, blazing at nearly 350,000 degrees Celsius. Yet surrounding it are dense knots of molecular hydrogen gas so cold and fragile it should have vaporized eons ago under that stellar inferno. How do these extremes coexist? Some suggest the lobes act as protective tunnels, shielding the molecules from the star's wrath, while others propose the knots are newer, formed from materials still being ejected. Then there's the nebula's secret third dimension. What looks like a simple two-lobed structure from Earth reveals, under spectroscopic analysis, a sprawling equatorial disk spinning like a cosmic carousel. This hidden ring, invisible in most images, might be the key to the Ant symmetry, a stabilizer for the bipolar jets, or perhaps the remnants of a stellar breakup we're only beginning to understand. Whether shaped by dueling stars or magnetic mayhem, the Ant Nebula stands as a testament to nature's ability to forge order from stellar chaos. And with every new observation, it asks us the same unanswerable question: how can something so precise emerge from a process so violent? The Saturn Nebula doesn't just mimic its planetary namesake, it outshines it with an otherworldly glow. NGC 7009, as astronomers catalogue it, hangs in the cosmos like a luminous emerald, its greenish hue so vivid it seems unnatural against the blackness of space. This isn't a trick of the light or an optical illusion. The nebula's eerie radiance comes from a rare and violent process happening at its core, where a dying star is tearing atoms apart with sheer cosmic force. At the heart of this spectacle lies a white dwarf, hotter than most furnace classifications could measure over 55,000 degrees Celsius at its surface. That extreme heat does something extraordinary to the surrounding gas. It strips oxygen atoms of not one, but two of their electrons, a state scientists call doubly ionized. These oxygen ions, now unstable and desperate to reclaim their lost electrons, release energy in the form of that unmistakable greenish light. It's a celestial neon sign powered by atomic chaos. But here's the catch: this phenomenon shouldn't be so bright. Most planetary nebulas glow faintly with this same oxygen emission, yet the Saturn Nebula's green dominates its entire structure, from the delicate loops at its poles to the jagged equatorial rings that give it its ringed planet appearance. Astronomers suspect the central star's temperature hits a sweet spot hot enough to ionize the oxygen aggressively, but not so hot that it destroys the gas entirely. It's like walking a cosmic tightrope, balancing destruction and illumination in a way few nebulas manage. Then there's the nebula's layered structure, which adds another puzzle. The green glow isn't uniform, it clumps and swirls, tracing shockwaves from the star's final eruptions. Some regions shine almost turquoise, where nitrogen and hydrogen mix with the oxygen, while others pulse with ultraviolet intensity, hinting at even heavier elements like neon lurking in the chaos. These variations suggest the dying star didn't shed its skin evenly. It coughed out material in fits and starts, leaving behind a chemical fingerprint of its death throes. What does this mean for our understanding of stellar evolution? The Saturn Nebula's glow is more than a pretty light show. It's a laboratory for extreme physics. By studying how that green light flickers and fades across the nebula, scientists can map the star's final millennia in reverse, piecing together how it lived and how it chose to die. And if one star can paint the void with such precision, what other atomic masterpieces might be hiding in the dark? The Medusa Nebula slithers through space not with a shout but a whisper. Officially catalogued as Able 21, this ancient remnant glows so faintly it tests the limits of our telescopes, its wispy tendrils visible only through hours-long exposures and meticulous image processing. This isn't your typical planetary nebula. It's a ghostly afterimage, the final breath of a star that died over 1,500 years ago, now stretched so thin its light barely registers against the cosmic backdrop. Unlike the vibrant hues of the Cat's Eye or Saturn nebulas, the Medusa's emission comes primarily from oxygen atoms stripped of 2 electrons, the same process that paints the Saturn Nebula green, but dialed down to a haunting monochrome glow. The difference: time. While younger nebulas blaze with energy from their freshly minted white dwarfs, the Medusa's central star has cooled to a dim ember, its radiation too weak to excite the surrounding gas into brighter displays. The result is a nebula that seems half-faded, like a photograph left too long in the sun. Observing it is like chasing a shadow. ground-based telescopes must contend with light pollution and atmospheric distortion, while even Hubble's keen eye struggles to capture its full extent without advanced filters. The nebula's most revealing portraits come from narrowband imaging, a technique that isolates specific wavelengths of light, amplifying the faint oxygen signal while suppressing the noise of the cosmos. Only then does the Medusa's true form emerge, a sprawling network of filaments, some twisted like serpents, others frayed at the edges like unraveling thread. Yet this faintness hides a violent past. Spectral analysis reveals the nebula's gas is racing outward at over 50 kilometers per second, a testament to the star's explosive death throes. The real puzzle: the gas isn't expanding evenly. Some regions billow outward in smooth arcs, while others kink abruptly, as if they'd collided with invisible barriers. Astronomers suspect interstellar dust or magnetic fields might be sculpting these irregularities, acting like celestial speed bumps for the outflowing material. Perhaps the most poignant detail is the nebula's gradual dissolution. Unlike younger planetary nebulas, which shine brightly for millennia, the Medusa is quietly disintegrating, its gas diffusing into the interstellar medium molecule by molecule. In another few thousand years, it may vanish entirely, leaving no trace of the star that once burned at its heart. For now, though, it lingers, a cosmic phantom, challenging us to piece together its story before it fades for good. The Owl Nebula stares back from the void with a gaze so hypnotic it's hard to believe it's not watching us. Officially catalogued as M97, this cosmic spectre earned its name from two eerie, dark patches that pierce its glowing shell like hollow eyes, an illusion so perfect it feels almost intentional. But these aren't just random voids, they're windows into one of the universe's most delicate balancing acts, where light and shadow conspire to create something hauntingly familiar. Peer closely at those eyes, and the illusion unravels into something far stranger. The darker patches aren't empty at all. They're regions where the nebula's thick hydrogen shell has thinned just enough to reveal the void behind it. Imagine holding a lantern inside a frosted glass globe, only to find two spots where the glass has worn thin, letting the darkness seep through. That's the owl's trick. Its glowing outer layers, excited by the radiation of its central white dwarf, shine brilliantly everywhere except where these mysterious gaps interrupt the light. But how did these gaps form? One theory points to stellar winds, fierce outflows from the dying star that punched through the shell like cosmic blowtorches, carving those iconic voids. Others suggest a more gradual process where uneven cooling caused parts of the shell to condense and collapse inward, leaving these eyes as natural weak points. The most tantalizing idea: a binary companion might be responsible. If the dying star had a smaller partner, its gravitational tugs could have destabilized the shell, creating asymmetrical thin spots that evolved into those perfect circles. Hubble's observations add another layer of intrigue. The edges of these dark patches glow faintly with ionized oxygen, suggesting the gaps aren't passive absences but active zones where energy leaks out in subtle ways. It's as if the owl's eyes aren't just watching, they're breathing, exhaling traces of the nebula's inner turmoil into space. And then there's the nebula's greater structure, which defies its serene name. Beyond the iconic face, the owl's outer layers churn with chaotic filaments and knots, remnants of the star's violent death throes. This isn't a peaceful cosmic portrait. It's a snapshot of chaos momentarily frozen into order, a fleeting alignment of physics and perspective that won't last forever. What does this mean for other planetary nebulas? The owl's illusion reminds us that even the cosmos plays tricks with light and shadow. Those dark eyes aren't just quirks of geometry, they're clues to the turbulent, unpredictable processes that shape stellar deaths. And if something as simple as a thinning shell can create such an uncanny resemblance to life, what other celestial faces might be hiding in the data, waiting for us to notice? The Stingray Nebula isn't just young, it's growing up before our eyes, designated HEN 31357. this cosmic infant holds the record as the youngest planetary nebula ever discovered, with observations revealing its dramatic metamorphosis in near real time. Just 2 decades ago, the Stingray was barely recognizable as a nebula at all, more of a faint, shapeless haze clinging to its central star. Fast forward to today, and it's blossomed into a vivid, structured spectacle, its curling tendrils and radiant core evolving faster than astronomers ever thought possible. What makes this transformation so extraordinary isn't just the speed, it's the defiance of cosmic norms. Most planetary nebulas take millennia to settle into their iconic forms, their slow expansions playing out over generations of human observation. But the Stingray, Hubble's snapshots caught it mid-metamorphosis, like a time lapse of a butterfly emerging from its cocoon. Between the 1990s and 2016, its temperature skyrocketed by over 30,000 degrees Celsius, while its once diffuse gas suddenly sculpted itself into distinct lobes and jets. This isn't just aging, it's cosmic hyperdrive. At the heart of this rapid evolution lies a star with an identity crisis. SAO 244267, the Stingray's central engine, wasn't supposed to become a white dwarf so soon. Originally classified as a humble B-type star, it unexpectedly ballooned into a red giant before abruptly shedding its outer layers, an accelerated life cycle that left astronomers scrambling to update their models. Some theorize the star's unusually low mass forced this rushed finale, like a candle burning too fast at both ends. Others suspect a hidden companion might have triggered premature ejections, pulling material away like a cosmic thief. The nebula's chemistry adds another layer of intrigue. Spectrographs revealed unexpected abundances of helium and nitrogen in its outer shells, elements typically forged deep within stars and released slowly over time. Their presence suggests the Stingray star didn't just shed its skin, it practically exploded it outward in a fit of stellar impatience, even more bizarre. The nebula's outer edges are already cooling, a process that usually takes tens of thousands of years. It's as if the Stingray is racing through its entire life cycle in fast forward, leaving scientists to wonder, is this a fluke or are we witnessing a new class of stellar death? Perhaps the most tantalizing question is what comes next. Most planetary nebulas shine brightly for millennia, but the Stingray's frantic pace suggests its glory may be fleeting. Some calculations predict its glow could fade to near invisibility within decades, a blink of an eye in cosmic terms. For now, though, it remains a living laboratory, challenging our assumptions about how stars live, die, and paint the cosmos with their final breaths. The Twin Jet Nebula spins through space like a cosmic ballet, its 2 vast gas streams spiraling in perfect opposition, a celestial pirouette set to the silent music of gravity. Officially known as M29, this nebula isn't just a static structure. It's a dynamic performance with twin jets stretching over 2.5 light years, each one a whirlwind of ionized gas hurtling outward at speeds exceeding 350,000 kilometers per hour. What sculpted this mesmerizing symmetry? The answer lies in a gravitational waltz between 2 stars locked in a fateful embrace. At the nebula's heart, a binary system plays puppeteer. A dying star, its outer layers already shed, orbits a smaller, more compact companion, likely a white dwarf. As the primary star ejects material in its death throes, the companion's gravity seizes control, funneling the gas into 2 narrow, opposing streams. But this isn't a simple tug of war. The star's orbital dance imparts a helical twist to the jets, like water from a spinning lawn sprinkler. Hubble's time-lapse observations reveal the jets aren't just flowing outward. They're corkscrewing through space, their delicate curls preserved for millennia in the vacuum. The real marvel is the precision of this chaos. Despite the violence of stellar death, the twin jets' outflows maintain near-perfect symmetry, their paths tracing elegant arcs that mirror each other across light years. Spectroscopic analysis uncovers even finer details, shockwaves ripple through the jets where faster material rams into slower ejections, creating glowing knots that pulse like cosmic waypoints. These aren't random collisions, they're rhythmic, echoing the binary pair's orbital period like a stellar metronome, yet the nebula guards its secrets fiercely. Infrared imaging exposes a thick, dusty torus girdling the central stars, a clue that the system's drama began long before the jets formed. Some theorists suggest this disk acted as a nozzle, collimating the outflows into those razor-sharp streams. Others point to magnetic fields wound tight by the star's rotation as invisible rails guiding the gas. The truth likely blends both, a reminder that even the universe's most beautiful patterns emerge from competing forces. What does this mean for other bipolar nebulas? The twin jets choreography suggests that binary stars might be the rule, not the exception, in shaping these structures. And if that's true, then every pinwheel of gas we spot in the cosmos could be a silent testimony to stellar partnerships, some harmonious, others turbulent, but all bound by gravity's unyielding hand. The Blue Snowball Nebula earns its name not from frost but from fire. Catalogued as NGC 7662, this cosmic gem blazes with an electric blue hue so intense it seems almost artificial against the void, a color born not from ice but from the searing fury of its central star. Unlike the soft pastels of many planetary nebulas, the blue snowball's radiance comes from a brutal atomic stripping. Helium atoms in its gas shell, bombarded by ultraviolet radiation so strong it tears away electrons with violent precision. What makes this celestial sapphire so vivid? The answer lies in the star's ruthless efficiency. At the nebula's heart, a white dwarf burns at over 75,000 degrees Celsius, unleashing UV photons energetic enough to ionize helium not once but twice. These doubly ionized helium atoms, missing both their electrons, release that iconic blue glow as they desperately recapture particles, a process so intense it outshines every other element in the nebula. It's like a cosmic neon sign powered by atomic desperation. But here's the twist: the blue snowball isn't uniformly blue. High-resolution images reveal a hidden emerald ring encircling its core, where oxygen ions add a subtle green tint to the outskirts. This chromatic layering acts as a stellar fingerprint, revealing the star's death in stages. The inner blue zone marks the most recent ejections, still bathed in the star's UV onslaught, while the outer green whispers of older material, cooling just enough to let oxygen's softer glow emerge. The real surprise: this nebula shouldn't be so small. Most planetary nebulas span light years, but the blue snowball's main shell measures a mere 0.1 light years across, a compact fury that suggests its central star shed its skin in abrupt, explosive bursts rather than a steady wind. Some theories point to a final thermonuclear convulsion, a last gasp eruption that ejected the star's outer layers in one dramatic heave. Others speculate a binary companion might have siphoned material until the system reached a breaking point, triggering a cataclysmic release. Yet the most puzzling detail is the nebula's filamentary tendrils, visible only through advanced filters. These wispy structures, glowing faintly with hydrogen, spiral outward like frozen smoke rings, evidence of earlier, quieter ejections before the star's final tantrum. It's as if the blue snowball preserved its entire death diary in light, from its first sigh to its last scream. What does this mean for other blue-hued nebulas? The snowball proves that stellar death isn't a monochrome process. Its vibrant palette, a marriage of violence and chemistry, reminds us that even in destruction, the cosmos paints with precision. And if one star's ultraviolet rage can craft something this breathtaking, what other atomic masterpieces might be lurking in the dark, waiting for the right light to reveal them? The Calabash Nebula doesn't just fade into the cosmic background, it reeks of celestial rebellion. Officially designated OH231.8, this turbulent cloud earned its nickname, the Rotten Egg Nebula, for a reason. Its gas shells brim with sulfur compounds, giving it a hypothetical stench that would curl the nose of any interstellar traveler. But what truly sets this nebula apart isn't just its foul chemistry, it's the sheer violence of its birth. Here, a dying red giant didn't just shed its layers, it erupted in a hypervelocity tantrum, flinging material outward at 700,000 kilometers per hour, fast enough to cross Earth's diameter in under 20 seconds. This isn't a gentle stellar farewell, it's a full-blown cosmic demolition. Hubble's sharp eye captured the calabash's chaos in stunning detail. Vast lobes of gas, twisted into hourglass shapes by opposing jets, while shockwaves ripple through the surrounding material like sonic booms frozen in time. At the nebula's heart, the red giant's core wages war against itself, convulsing as it transitions into a white dwarf. The result, a fireworks show of molecular destruction, where sulfur monoxide and hydrogen sulfide, chemicals more at home in a volcano's plume, mix with the usual stellar ejecta. What could trigger such extreme eruptions? The leading theory points to a stellar swan song gone wrong. As the red giant exhausted its nuclear fuel, its core began collapsing unevenly, like a building imploding floor by floor. This instability may have triggered runaway thermal pulses, each one blasting away chunks of the star's atmosphere in violent spasms. Spectrographs reveal these ejections weren't smooth. They came in frantic bursts, layering the nebula with clumps and filaments that resemble shrapnel from a celestial grenade. The real puzzle lies in the nebula's asymmetry. Unlike the precise jets of the twin jet nebula or the symmetrical rings of the Ring Nebula, the calabash's outflows skew wildly off-axis, as if the star was knocked sideways during its death throes. Some astronomers suspect a stealthy companion star lurking just out of view might have yanked the dying giant off balance, its gravity distorting the ejections into those chaotic lobes. Others propose the star's own magnetic field, tangled beyond recovery, funneled material into these erratic streams. Yet the most startling discovery might be the calabash's temperature swings. While most planetary nebulas glow from heated gas, this one harbors bizarre cold spots, regions where molecules like sulfur dioxide huddle together, barely warmed by the central star's fading light. It's a cosmic contradiction, a nebula simultaneously searing and frigid, its chemistry oscillating between creation and decay. What does this mean for other sulfur-rich nebulas? The calabash forces us to reconsider how stars die, not always with orderly elegance, but sometimes with a volatile, elemental roar. Its rotten egg signature isn't just a quirk, it's a testament to the untamed physics of stellar demise, where even the universe's most predictable endings can spiral into beautiful catastrophe. The ghost of Jupiter Nebula plays a cosmic game of hide and seek with astronomers, its glowing visage fading in and out of view like a celestial mirage. Officially catalogued as NGC 3242, this planetary nebula earned its haunting nickname not just from its resemblance to Jupiter's disk, but from its eerie ability to vanish before the eyes of amateur stargazers. One moment it's there, a shimmering, greenish orb floating against the darkness, and the next it's gone, dissolved into the background as if swallowed by the night itself. This vanishing act isn't magic, it's a quirk of structure. While the nebula's core blazes with enough intensity to outshine most of its peers, its outer shells are impossibly diffuse, stretching so thin they flirt with invisibility. Picture a lighthouse beacon surrounded by fog. Up close, the light dominates, but step back and the mist swallows it whole. That's the ghost of Jupiter's trick. Its heart, energized by a white dwarf hotter than 90,000 degrees Celsius, pumps out enough ultraviolet radiation to make the inner shell glow like a neon sign. But venture outward, and the gas thins to near nothingness, its atoms too sparse to reflect much light at all. The real mystery lies in why these outer layers are so tenuous. Most planetary nebulas eject their material in dense waves, creating sharp boundaries between gas and void. Not this one. Spectral analysis reveals its outer shells are more like smoke than solid structure, wisps of hydrogen and oxygen stretched across light years by forces we're still deciphering. Some theorize the dying star's final outbursts were unusually gentle, like a sigh rather than a scream, allowing the gas to drift outward without forming clumps. Others point to interstellar winds whipping through the nebula's edges and shearing them into near invisibility. Then there's the observational quirk that makes this ghost so elusive to backyard telescopes. Unlike nebulas with crisp edges which snap into focus under magnification, the ghost of Jupiter's diffuse halo requires averted vision, a stargazing technique where observers look slightly beside the target, allowing their peripheral vision's light-sensitive rods to detect the faint glow. It's a cosmic irony. The harder you stare, the more it disappears. But perhaps the most haunting detail is what this means for the nebula's future. With outer shells this delicate, the ghost of Jupiter won't linger for millennia like younger, denser nebulas. Instead, it's quietly dissolving, its outer layers already blending into the interstellar medium. In time, only the brilliant core will remain, a lone specter against the dark until even that winks out. For now, though, it lingers, a fleeting masterpiece of light and nothingness, challenging us to glimpse it before it's gone for good. The little dumbbell nebula sounds like a cosmic afterthought, some small, forgettable trinket lost in the vastness of space. But don't let its modest name fool you. M76, as astronomers catalogue it, is a shape-shifting enigma, its structure so intricate it mocks the simplicity of its nickname. Peer through a telescope and you'll see not a single dumbbell but a labyrinth of glowing gas, where twin lobes collide with equatorial rings in a celestial ballet of light and shadow. Hubble's gaze reveals the nebula's true complexity. Two bright, asymmetrical lobes, each a blistering cocoon of ionized gas, stretch outward like wings, while a faint, ghostly ring girdles their center as if holding the chaos together. This isn't just a dying star's farewell, it's a multi-act drama with each structure telling a different chapter of the star's demise. The lobes, racing outward at nearly 50 kilometers per second, are littered with shockwaves where fast-moving ejections slam into slower material. The result, a network of glowing filaments twisted like frayed rope, each one a fossilized record of the star's violent outbursts, yet the real mystery lies in that central ring. Unlike the crisp, geometric halos seen in younger nebulas, M76's ring is warped and uneven, its material clumped in dense knots that defy explanation. Some astronomers believe it's the remnants of a red giant's slow, pre-death wind, compressed into a disk by magnetic fields. Others argue it's evidence of a binary companion's gravitational meddling, its invisible fingers sculpting the gas into this tortured shape. Infrared observations add fuel to the debate, revealing molecules like hydrogen cyanide embedded in the ring, chemicals normally found in star-forming regions, not stellar graves. Then there's the nebula's most baffling feature, the missing lobe. While most bipolar nebulas show symmetry, M76's eastern lobe shines noticeably dimmer than its western counterpart. Is it obscured by interstellar dust, or did the dying star eject material unevenly like a sputtering engine? The answer might lie in the nebula's turbulent past. Spectrographs detect strange velocity shifts in the gas, hinting at ancient stellar convulsions that might have knocked the entire system off balance. What does this mean for other so-called simple nebulas? The little dumbbell's hidden complexity forces us to reconsider how we label cosmic phenomena. Its name, born from 19th century observations, barely scratches the surface of its true nature, a reminder that even the most familiar objects in space can harbor secrets that defy expectations. So the next time you hear dumbbell, think again. This nebula isn't just lifting weights, it's rewriting the rules of stellar death. The Necklace Nebula dazzles like a celestial treasure chest flung open across the cosmos, its glowing loops strung with what appear to be cosmic diamonds. Catalogued as PNG 54.2-03.4, this rare gem of a nebula didn't form from gentle stellar winds. It's the aftermath of a violent stellar heist, where one star devoured its companion in an act of gravitational cannibalism. At first glance, those glittering knots seem too perfect to be natural. Each diamond in the necklace is actually a colossal clump of gas, some spanning twice Earth's orbit, glowing under the ultraviolet onslaught of the surviving star. But their symmetry is no accident. When the primary star ballooned into a red giant, it engulfed its smaller binary partner, which spiraled inward like a moth drawn to a flame. The companion didn't go quietly. Its death plunge whipped the giant's outer layers into a frenzy, ejecting material in a dense equatorial ring studded with dense knots. Think of a spinning pizza dough flung outward, but instead of thinning evenly, it fractured into radiant droplets frozen in space. Hubble's razor-sharp vision reveals even wilder details. The central star rotates so fast it's flattened into an oblate spheroid, its equator spinning at over 300,000 kilometers per hour, a speed so extreme it's flinging material off into space like a stellar sprinkler. This dizzying spin is the thief's telltale signature. The energy stolen from the consumed companion supercharged the survivor, turning it into a cosmic centrifuge. Yet the real marvel is the chemistry. Spectroscopy uncovered surprising amounts of nitrogen and oxygen in those gaseous jewels, elements typically buried deep in stellar cores. Their presence suggests the companion's demise dredged up material from both stars' interiors, mixing their atomic essence into these luminous beads. It's as if the nebula forged its jewels from the ashes of a double tragedy, each gem a monument to the star's final embrace. What does this mean for other tight binary systems? The Helix Nebula is a rare snapshot of stellar vampirism caught mid-process, proving that even the universe's most beautiful creations can emerge from chaos. And if one cataclysm can string the void with diamonds, what other celestial jewelry might be hiding in the dark, waiting for the right light to reveal it? The soccer ball nebula floats through space with geometric perfection. Its spherical shell, so flawlessly rounded, could have been inflated by cosmic hands. Officially known as Cronberger 61, this celestial oddity defies the usual chaotic artistry of planetary nebulas, presenting instead as a near-perfect bubble of ionized gas, a structure so precise it seems almost artificial. While most nebulas twist into intricate spirals or jagged lobes, this one glows with the symmetry of a child's drawing, its edges crisp, its form unblemished. What sculpted this unnatural sphere? The answer lies in the quiet death of an unusually cooperative star. Unlike the violent binary systems that carve nebulas into butterflies or hourglasses, Cronberger 61's central star appears to have died alone, shedding its outer layers in a steady, even wind. Without a companion star's gravitational tugs or magnetic mayhem to distort the outflow, the gas expanded uniformly in all directions, like a balloon inflating in slow motion. But here's the catch: such perfect symmetry shouldn't exist. Even solitary stars typically have surface irregularities, sunspots, flares, or rotational bulges that imprint slight asymmetries on their dying breath. Yet Cronberger 61's shell shows no dents, no warps, no deviations. Some theorists speculate the star might have spun unusually slowly, its calm rotation preventing any equatorial bulging that could have skewed the ejections. Others wonder if an unseen magnetic field, perfectly aligned, acted as an invisible mold, shaping the gas into this impossible geometry. The nebula's glow adds another puzzle. Most spherical nebulas radiate faintly, their gas too diffuse to shine brightly. But the soccer ball burns with unexpected intensity, its oxygen-rich shell fluorescing under the central star's ultraviolet glare. Spectrographs reveal a strange disconnect. The gas is far denser near the edges than at the core, as if the star's final eruptions were front-loaded, ejecting most of its material early on before tapering off. This inverted density gradient might explain the nebula's crisp edges like a soap bubble with its thickest film on the outside. Perhaps the most tantalizing clue is the nebula's youth. Unlike the ghost of Jupiter or the Medusa, Cronberger 61 is a cosmic toddler. Its central star only recently collapsed into a white dwarf. This means we're catching it at a rare moment before interstellar winds or internal instabilities have had time to warp its pristine shape. In a few thousand years, even this perfect sphere might fray at the edges, its symmetry succumbing to the universe's relentless entropy. For now, though, the soccer ball nebula remains a cosmic conundrum, a reminder that even in death, stars can achieve a quiet, fleeting perfection. And if one star can bow out with such geometric grace, what other undiscovered marvels might be hiding in the void, waiting for us to notice their hidden order? The lemon-sliced nebula gleams in the cosmos like a drop of citric light suspended in the void, a seemingly simple sphere of gas so smooth and uniform it defies the usual chaos of stellar death. Officially designated IC 3568, this cosmic enigma presents astronomers with a puzzle. How can something so brutally hot appear so deceptively serene? At first glance, it's all calm radiance, its edges blurred into a soft halo without the intricate filaments or shockwaves seen in most planetary nebulas. But peer closer and the illusion shatters. At the heart of this tranquil facade rages a stellar furnace unlike almost any other. The central star burns at a staggering 90,000 degrees Celsius, blasting its surroundings with ultraviolet radiation so intense it strips electrons from atoms with ruthless efficiency. What makes this star extraordinary isn't just its temperature, it's the way that heat behaves. Most white dwarfs at this stage pump energy into their nebulas, creating intricate structures of glowing gas. Yet the lemon slice's radiation disperses almost evenly, like light through frosted glass, leaving the surrounding nebula eerily smooth. The nebula's lack of texture isn't a sign of simplicity, it's a clue to a violent past. Spectroscopic analysis reveals the gas is racing outward at over 30 kilometers per second, hinting at explosive ejections that should have left behind clumps or ripples. So where's the turbulence? One theory suggests the star's death throes were oddly uniform, as if it shed its skin in a single, controlled burst like a fruit peeled in one perfect spiral. Another possibility points to an invisible force, perhaps a magnetic field so perfectly aligned it funneled the ejections into this flawless sphere, smoothing out irregularities like an iron pressing wrinkles from fabric. Then there's the star itself, which refuses to fit neatly into classification. Its spectrum shows bizarre absorption lines, suggesting an atmosphere choked with heavy metals that shouldn't linger at such temperatures. Normally, a white dwarf this hot would have blown away these elements like dust in a hurricane. Their persistence implies something stranger. The star might be dredging up material from its own depths, like a dying ember spitting out one last shower of sparks. What does this mean for other featureless nebulas? The lemon slice proves that smoothness can be deceptive, a cosmic sleight of hand hiding ferocious physics. Its serene glow isn't the mark of a quiet death, but a tombstone for a star that burned too bright, too fast, and left behind a relic too perfect to be accidental. In the end, it's not a lemon at all, it's a rind, hollowed out by fire, glowing with the aftermath of a stellar life we're only beginning to understand. The engraved Hourglass Nebula doesn't just mimic time's relentless flow, it obeys forces far stronger than gravity alone. Mycene 18, as it's catalogued, presents one of the cosmos' most perfect hourglass shapes, its pinched waist so precise it seems sculpted by invisible hands. But this astronomical artistry isn't just the work of stellar winds or binary companions. It's the product of magnetic fields so powerful they strangle the nebula's outflow like cosmic corset strings. At first glance, the nebula's symmetry seems too perfect to be natural. Twin lobes of glowing gas expand outward, their curvature flawless, while the central waist contracts to a filament-thin bottleneck. Hubble's ultraviolet images reveal why. Nested within those glowing streams are magnetic field lines, twisted into helical coils by the dying star's rapid rotation. These fields don't just guide the gas, they choke it, funneling the outflow into those iconic narrow jets with forces comparable to 1,000,000 Earth magnets packed into a space no wider than our solar system. Spectrographic data paints an even wilder picture. The waste region crackles with polarized light, a telltale signature of magnetic dominance, while the gas itself races outward at speeds exceeding 150 kilometers per second, only to slam into the field's invisible barrier. The result, shockwaves that glow brightest where the struggle between gas and magnetism is fiercest, creating that radiant hourglass silhouette. It's as if the nebula is caught in a cosmic tug of war, with magnetic forces winning by a hair. Yet the real surprise lies in the field's origin. Most planetary nebulas derive their magnetism from binary companions or accretion disks, but Mycian 18's central star spins solo. Instead, astronomers suspect the star's own demise spun its magnetic field into overdrive. As the star collapsed into a white dwarf, its rotation accelerated, like a figure skater pulling in their arms, winding its magnetic field tighter until it became a vice grip on the ejected gas. What does this mean for other pinched nebulas? The engraved hourglass suggests that even lone stars can sculpt their deaths with precision when magnetism takes the reins. And if one star's invisible fields can carve the void into something this exquisite, what other unseen forces might be shaping the cosmos in ways we've yet to imagine? The frosty Leo Nebula doesn't just shimmer, it glistens with a celestial frost unlike anything else in the cosmos. Officially catalogued as ERA's 09371+1212, this remote wonder earned its wintry nickname from an extraordinary feature. Its dust grains are literally encased in ice, glowing in infrared light like a blizzard frozen in time. Picture a cosmic snow globe where every speck of dust wears a microscopic coat of frozen water, methane, and carbon monoxide molecules usually vaporized by starlight. Yet here they cling stubbornly to existence in the nebula's frigid embrace. What makes these icy grains so bizarre isn't just their existence, it's their defiance of physics. The frosty Leo's central star burns hot enough to scorch its surroundings, yet the surrounding dust remains stubbornly frosty. The secret: distance. The nebula's dust shell orbits so far from the star that temperatures plummet to nearly -260 degrees Celsius, cold enough to preserve ice even under the star's feeble warmth. Infrared telescopes reveal these grains in stunning detail, their crystalline structures reflecting light like a field of diamonds scattered across the void. But the real marvel lies in the chemistry. These aren't simple water ice coatings. Spectrographs detect complex organic molecules like formaldehyde and hydrogen cyanide trapped within the frost, compounds typically associated with the birth of planets, not the death of stars. It's as if the frosty Leo Nebula is a cosmic freezer, preserving ingredients for life in its icy vaults long after its star's fiery demise. Some theories suggest these grains might even survive the nebula's eventual dissipation, seeding future generations of star systems with their frozen cargo. Then there's the nebula's most haunting feature, its silence. Unlike younger planetary nebulas crackling with energetic outflows, the frosty Leo's expansions are slow, its winds gentle, a glacial pace that allows the ice to form and persist. This quietude makes it a fossil of sorts, a relic of stellar death where time moves differently, and the universe's usual violence gives way to an almost meditative stillness. What does this mean for our understanding of cosmic chemistry? The frosty Leo challenges the assumption that stellar deaths are purely destructive. Instead, it hints at a universe where even in endings there's preservation, where ice and dust might outlast fire and light, carrying whispers of ancient stars into the unknown future. The Peanut Nebula doesn't just float in space, it pulses with the hidden rhythm of a stellar dance few ever witness. Officially catalogued as M192, This cosmic oddity earned its snack food nickname from its distinctive dual-lobed shape, two bulbous protrusions pinched at the center like the shell of its namesake. But the real story isn't just in the lobes, it's in the celestial tango happening inside them. Nestled within that dusty waistline, two stars orbit each other in a gravitational embrace so tight it sculpts the entire nebula into its peculiar form. At first glance, the peanut looks like many other bipolar nebulas, twin jets of gas streaming from a central engine. Yet what sets it apart is the thick, obscuring belt of dust wrapping its middle like a cosmic corset. This isn't just debris, it's the smoking gun of stellar interaction. As the primary star began its death throes, swelling into a red giant, its outer layers became vulnerable to the gravitational pull of its smaller companion. The result, a violent game of tug-of-war where the companion star siphoned material into a swirling accretion disk, then funneled the excess outward in opposing jets, carving those iconic lobes with stellar precision. Infrared observations pierced the dust veil, revealing the true architects of this chaos. The central binary system whirls so close that their orbital period clocks in under a century, a blink of an eye in cosmic terms. Every rotation tugs the gas streams, warping them into subtle spirals detectable only through Doppler shifts in their light. It's like watching two dancers in a darkened room, their movements traced only by the swirl of their costumes. The real marvel lies in the lobe's asymmetry. While many bipolar nebulas mirror themselves neatly, the peanut's eastern lobe stretches farther and glows brighter than its western counterpart. Some astronomers attribute this lopsidedness to the companion star's off-center orbit, its gravity yanking harder on one side than the other. Others point to interstellar winds blowing against the nebula like a cosmic breeze bending a flame. Yet the most tantalizing clue hides in the dust itself. Spectrographs detect crystalline silicates minerals usually found in planetary crusts, not stellar graves embedded in those dense equatorial rings. This suggests the peanut stars didn't just eject gas, they forged solid stardust atom by atom in their dying breaths. It's a reminder that even in endings, creation persists, and sometimes it leaves behind something as strangely beautiful as a cosmic peanut. The Cotton Candy Nebula spins through space like a confectionery nightmare, its wispy tendrils fraying at the edges as if unraveling in real time. Officially catalogued as NGC 7027, this cosmic spectacle looks nothing like the serene, symmetrical nebulas we're used to instead. It's a maelstrom of hyperactive gas where shockwaves crisscross at speeds that would reduce sound to a whisper. Picture a cloud of spun sugar caught in a hurricane, its delicate strands whipped into chaos by forces unseen. What makes this nebula's fluff so extraordinary is the violence hiding beneath its deceptively soft appearance. Hubble's razor-sharp images reveal a reality far removed from cotton candy's sweetness. Supersonic jets of material, blasting outward at nearly 600,000 kilometers per hour, collide with slower-moving gas in explosive fronts. These aren't gentle collisions, they're cosmic train wrecks, generating temperatures hot enough to melt steel and pressure waves that ripple through the nebula's structure like tsunamis in slow motion. The result, a fractal frenzy of filaments, each one a fossilized echo of a stellar tantrum frozen in gas. The nebula's core is even wilder. Nestled inside this gaseous frenzy, the central star wages war against itself, ejecting material in erratic bursts that leave behind concentric shells of debris, like the layers of an onion carved by a chainsaw. Spectrographs detect bizarre chemical signatures in these layers, including helium hydride, the very first molecule to form in the early universe. Its presence here is a cosmic irony, a relic of creation forged anew in the fires of destruction. But the real shock is how young this chaos is. Unlike sprawling nebulas that take millennia to settle, NGC 7027 is a cosmic infant, its dramatic transformations playing out over mere centuries. Observations suggest the star's death throes began in earnest around the year 600 AD, making this one of the freshest stellar remnants we've ever witnessed. Every new telescopic image captures a slightly different shape, as if we're watching time-lapse footage of a star's self-destruction. What does this mean for other fluffy nebulas? The cotton candy's turbulence challenges the very definition of planetary nebulas, proving that stellar death can be as messy as it is majestic. Its ever-changing form whispers a question. If one star's demise can paint the void with such fleeting, fractal beauty, what other ephemeral masterpieces might we be missing in the dark? The Water Lily Nebula drifts through space like a ghostly blossom, its delicate tendrils glowing with an otherworldly blue hue. But this isn't just any cosmic flower. Officially designated U4, this sprawling structure stretches over 2.5 light-years, dwarfing most planetary nebulas with its sheer scale while remaining so faint it eluded discovery until 2011. What makes this celestial bloom truly extraordinary isn't just its size or its haunting glow. It's the secret ingredient lighting it up: oxygen atoms stripped bare by radiation, their electrons violently ripped away, leaving behind an eerie luminescence that pulses with the echoes of stellar death. Most nebulas shine from the heat of their central stars, but the water lily's glow comes from a far stranger process. Deep within its filaments, oxygen atoms endure a relentless atomic assault, bombarded by ultraviolet radiation so intense it excites them into a fluorescent frenzy. The result, a nebula that glows not from fire but from atomic desperation, a phenomenon so rare it's been spotted in only a handful of structures across the cosmos. This isn't just light, it's the scream of atoms trapped in an invisible storm, their energy bleeding into the void as that haunting azure light. Yet the real mystery lies in the nebula's origins. Unlike the Butterfly or Ant Nebula, U4 lacks a clearly visible central star. Some theories suggest it might be the remnant of a monstrous hypergiant, its eruptions so violent they scattered material too thinly for a traditional core to dominate. Others propose a runaway white dwarf, ejected from its birth system and now hurtling through space, leaving its glowing wake behind like a cosmic contrail. The most tantalizing clue, the nebula's bizarre bipolar jets detected in radio wavelengths, which twist outward in opposite directions at speeds exceeding 600 kilometers per second, a fingerprint of some cataclysmic yet unseen stellar disruption. Then there's the nebula's most perplexing feature, its silence. Despite its staggering size, the water lily emits almost no infrared or X-ray signals, the usual hallmarks of energetic nebulas. Instead, it whispers to us in narrowband oxygen light, a spectral fingerprint so specific it took years of painstaking observation to confirm its existence. It's as if this nebula exists in a parallel dimension of the electromagnetic spectrum, visible only through the narrowest of atomic windows. What does this mean for other invisible nebulas? The water lily challenges our very definition of planetary nebulas, proving that stellar deaths can paint the cosmos in light our eyes were never meant to see. Its tendrils, glowing with radioactive elegance, remind us that the universe's most breathtaking spectacles often hide in plain sight, waiting for the right technology, the right moment, and the right gaze to bring them into focus. The Egg Nebula doesn't just glow, it whispers to us across light years, its secrets encoded in ripples of light that pulse outward like echoes in a cosmic canyon. Officially catalogued as CRL 2688, this bizarre structure hides a time lapse of stellar death within its concentric dust shells, each one a reflective canvas catching the dying star's final flickers. Unlike most nebulas where gas emits its own light, the egg's eerie beauty comes from something far stranger, starlight bouncing off dust like a flashlight beam in a hall of mirrors, creating ghostly afterimages that lag behind the original flash by centuries. At the heart of this phenomenon lies a star in crisis. As it shed its outer layers, it didn't go quietly. Instead, it erupted in sporadic bursts, each flash of light racing outward at, well, the speed of light. But here's where physics gets poetic. Those light waves hit successive shells of previously ejected dust, illuminating them in delayed succession. The result? A series of glowing rings expanding outward, each one a snapshot of the star's death spasms frozen at different moments in time. It's like watching a stellar echo chamber where the past reverberates in luminous slow motion. Hubble's images reveal these echoes in stunning detail. The innermost rings, hot and bright, trace the star's most recent eruptions, while fainter, outer rings preserve outbursts from hundreds of years earlier. By measuring the spacing between these rings, astronomers have reconstructed a timeline of the star's death throes, a stellar autobiography written in concentric light. But the real shock came when they noticed the rings weren't perfect. Some kink abruptly, others fray at the edges, betraying violent encounters with interstellar winds or perhaps the gravitational tug of an unseen companion. The nebula's polar jets add another layer of mystery. Twin cones of gas ejected at nearly 150,000 kilometers per hour punch through the dust shells, their paths warped by magnetic fields into corkscrew spirals. These jets interact with the light echoes in bizarre ways, casting shadows that stretch across the nebula like cosmic sundials. In some regions, the dust is so thick it smothers the echoes entirely, creating dark voids where the star's history remains stubbornly veiled. What makes the egg truly unique is its fleeting nature. Unlike the static glow of most nebulas, these light echoes are transient, expanding and fading as the original flashes grow dimmer with distance. In another few centuries, the innermost rings will have dissipated entirely, leaving only the faintest traces of the star's final cries. For now, though, the Egg Nebula offers us a front-row seat to stellar death in slow motion, proving that even in its last moments, a star can paint the void with echoes of its own unraveling. The Spirograph Nebula spins through space like a celestial etching, its delicate walls and concentric rings so precise they seem drawn by cosmic compasses. Catalogued as IC418, this radiant structure could easily be mistaken for an artist's intricate sketch, except no human hand could replicate its scale or complexity. Stretching nearly half a light-year across, its luminous patterns ripple outward with geometric perfection, each band a frozen echo of the star's rhythmic death throes. What carves such flawless symmetry into the void? The leading theory points to stellar pulsations, slow, seismic beats from the central star as it sheds its outer layers. Imagine a heartbeat translated into light. Every few decades, the star's core convulses, ejecting material in synchronized waves. These spherical shells expand outward, stacking like layers of an onion, each new eruption pressing against the last. Hubble's ultraviolet eyes reveal the stunning result, a nested series of glowing rings. Their spacing so uniform it hints at clockwork precision in the star's demise. Yet the nebula's beauty hides violent physics. The central star, a white dwarf hotter than 36,000 degrees Celsius, bombards these ejections with ultraviolet radiation, exciting the gas into fluorescence. Oxygen atoms, stripped of electrons, glow teal where they collide with slower-moving hydrogen, tracing shock fronts that look deceptively serene from afar. The real magic lies in the details. Spectroscopic analysis uncovers subtle kinks in those perfect rings, evidence of magnetic fields twisting the outflow like invisible fingers dragging through wet paint. The spirograph's most tantalizing secret: its patterns aren't static. Comparing Hubble images taken years apart shows the rings expanding at 19 kilometers per second, fast enough to cross Earth's diameter in under 20 minutes. By measuring this growth, astronomers have reverse-engineered the star's pulse schedule, discovering its outbursts occur roughly every 280 years. That regularity defies expectations. Most dying stars expel material in chaotic bursts. Some suspect a binary companion's gravitational metronome keeps the rhythm, while others argue the star's own internal oscillations act as a cosmic pendulum. Then there's the nebula's unexpected chemistry. Embedded within its rings are molecules like polycyclic aromatic hydrocarbons, complex carbon compounds usually found in stellar nurseries, not graves. Their presence suggests the dying star isn't just destroying itself, it's forging ingredients for future cosmic creation, weaving death and rebirth into a single glowing tapestry. What does this mean for other patterned nebulas? The spirograph proves that stellar death need not be chaotic, that under the right conditions, stars can bow out with mathematical grace. Its rings stand as frozen music, a stellar symphony written in light and gas, waiting for us to decipher its notes. And if one star's final act can paint the cosmos with such precision, what other hidden rhythms might be pulsing unseen across the universe? The Mimosa Nebula glows softly in the night sky like a dying ember, its delicate tendrils of gas stretching outward in quiet surrender. But it's what's happening at its core that has astronomers leaning in closer. NGC 4361, as it's formally catalogued, harbors a central star that's dimming at a rate no model predicted, fading faster than a candle wick drowning in wax. This isn't just a star burning out. It's a stellar farewell that defies every expectation of how planetary nebulas evolve, rewriting the final chapter of a sun-like star's life in real time. At the heart of the Mimosa Nebula, a white dwarf that should be searingly bright instead flickers like a faulty street lamp. Theoretical models suggest stars of its size and composition should stabilize after ejecting their outer layers, shining steadily for millennia as they cool. Yet observations reveal this star's luminosity has dropped by nearly 40% in just the past century, a blink of an eye in cosmic terms. Spectrographs tell an even stranger story. The star's surface temperature, instead of gradually decreasing, has plummeted in erratic fits and starts, as if something unseen is siphoning away its energy. One leading theory points to a cosmic thief, a previously undetected companion star or substellar object skimming material from the white dwarf's atmosphere and accelerating its cooling. But Hubble's sharp gaze finds no visible partner, leaving astronomers to speculate about darker possibilities. Could an accretion disk of debris, invisible to optical telescopes, be sapping the star's warmth? Or is the white dwarf's own magnetic field twisted into knots during its death throes, trapping heat beneath an insulating shell like a stellar thermos? The nebula itself adds another layer of intrigue. While most planetary nebulas expand and dissipate over tens of thousands of years, the Mimosa's delicate filaments show signs of premature cooling, their oxygen-rich tendrils glowing fainter with each passing decade. Radio telescopes have detected bizarre pockets of molecular hydrogen, a gas normally ripped apart by stellar radiation lurking in the nebula's outer reaches, untouched by the central star's waning ultraviolet fury. It's as if the nebula is freezing over, its gases settling into a cosmic frost even as the star at its heart dims. What does this mean for other aging nebulas? The Mimosa's rapid fade suggests our models of stellar afterlife might be missing a critical piece, perhaps a hidden phase where white dwarfs can cool unpredictably, or mechanisms that drain their energy faster than physics allows. If one star can bow out this quickly, how many others have we misjudged? For now, the Mimosa Nebula keeps its secrets, its fading light a silent challenge to our understanding of how stars truly die. The Jack-O-Lantern Nebula glows in the void like a cosmic Halloween decoration, its gourd-like shape an eerie orange hue making it one of the most visually striking structures in the galaxy. Officially catalogued as ERAS 17163-3907, this celestial pumpkin wasn't carved by knives but by the relentless scouring of stellar winds, a natural sculpture crafted by the fury of its central star. At first glance, the resemblance is uncanny, a nearly spherical shell of dust and gas, pinched at the poles and pockmarked with darker patches that mimic the jagged eyes and mouth of a jack-o'-lantern. But this isn't just a seasonal coincidence, it's a masterpiece of astrophysics where chaos and symmetry collide in unexpected ways. What shapes this stellar gourd? The answer lies in the star's violent tantrums. Nestled at the nebula's core is a hypergiant, a behemoth so massive it makes our sun look like a speck of dust. This star doesn't just burn, it rages, ejecting material in furious bursts that collide with slower-moving gas expelled during earlier, quieter phases. The result, a luminous outer shell heated to incandescence by the star's ultraviolet fury, while denser knots of dust resist erosion, casting shadowy, carved features against the glowing backdrop. Imagine a candle inside a pumpkin, but replace the flame with a star that could vaporize planets, and the pumpkin's walls with a superheated shroud of cosmic debris. Infrared observations reveal even stranger details. The nebula's iconic orange glow comes from a mix of ionized sulfur and warm dust, but its outer layers hide a secret, vast tendrils of cooler material, stretching far beyond the visible structure like the frayed edges of a poorly stitched costume. These filaments, invisible to optical telescopes, trace the paths of ancient stellar winds, gusts that blew millions of years before the star reached its current volatile state. It's as if the jack-o'-lantern is wearing a tattered cloak, remnants of its quieter past still clinging to its fiery present. The most haunting detail, though, is the nebula's asymmetry. Unlike the perfectly round shapes of younger planetary nebulas, this one bulges slightly at its equator, as if squeezed by invisible hands. Astronomers suspect this distortion comes from the star's rotation, spinning so fast it flings material outward unevenly, like a figure skater spreading their arms, but with the arms replaced by supersonic jets of plasma. Add to that the relentless push of interstellar winds, and you've got a cosmic pumpkin that's been slightly squashed by the universe itself. What makes this nebula truly special isn't just its festive appearance, it's the reminder that even in the cold, indifferent void of space, nature has a flair for the theatrical. The Jack-o'-lantern Nebula didn't set out to mimic a Halloween icon. It's simply the result of a star's death throes playing out under the right conditions. And yet, here it is, a grinning, glowing specter in the dark, proving that sometimes the universe's artistry is stranger than anything we could dream up ourselves. From the Butterfly Nebula's symmetrical chaos to the frosty Leo's icy whispers, these 30 wonders prove planetary nebulas are anything but predictable. They're cosmic shape-shifters defying physics with hypervelocity jets, rewriting stellar life cycles in real time, and hiding chemical cocktails that shouldn't exist. Who would have guessed a dying star could sculpt ice-encased dust grains or forge a perfect soccer ball in the void? Or that a nebula could flicker like a failing light bulb, its central star vanishing faster than our models can explain? Every discovery peels back another layer of mystery, revealing how much we still don't understand about these radiant stellar graves. Perhaps the most humbling lesson is how wrong we've been. Planetary nebulas aren't just dying stars' funeral shrouds, they're laboratories for extreme physics. Artist studios where magnetic fields and binary dances paint the cosmos in neon. They birth molecules that could seed life elsewhere, preserve stellar echoes for millennia, and even mimic Halloween pumpkins with unsettling accuracy. And just when we think we've seen it all, something like the Stingray Nebula evolves before our telescopes, aging faster than a time lapse, or the Water Lily Nebula glows in atomic frequencies barely visible to our instruments. Now it's your turn. Which of these cosmic rebels left you speechless? Was it the Red Spider's poisonous chemistry, the necklace's stolen stellar diamonds, or the ghost of Jupiter's vanishing act? Drop your pick in the comments and let's geek out over the universe's weirdest art gallery together. And if you're hungry for more celestial mysteries, hit subscribe. We're just getting started unraveling the cosmos' greatest enigmas. Until next time, keep looking up, because out there, even the laws of physics love a good plot twist.